Hey everyone. So here is a video for our 1.2 lesson for today. My apologies, I couldn't be there. I had an appointment. So we've already introduced this 1.2 lesson. It was on the same day we talked about conjugates, and we didn't have any homework for it. So we're actually going to finish this off and formalize it now that we know a lot more about limits. And you'll understand why I left it till now, because we needed all that limit practice before we can tackle this. So to start 1.2, we were looking for what is the instantaneous velocity at 0.5. Essentially, we were asking, when this ball was thrown up, we were asking at 0.5, what was the slope of the tangent, is the question we were trying to answer. And so the strategy we took was, instead of, because on this last page here, we kind of went to 1/100th away from on the right and 1/100th away on the left and calculated, and we seem to be getting close to 13. And we can go a lot closer. But we didn't want to have to reset to the beginning, like a beginning slope calculation, y equals mx plus b, like you see right here. Okay, so this is just a slope calculation, or y2 minus y1 over x2 minus x1. We didn't want to have to reset all the way back to the slope formula every single time. So the strategy we took is we said, okay, well, let's do that slope calculation in general. So here's our y2 minus y1 over x2 minus x1, except we made our x1, sorry, our x2, y2, we made them be t1, comma, and then what the function was, because that's what y is equal to anyway. We knew y was equal to this function. So we used the entire function, and it's simplified to give us this slope formula now. So this is a slope formula. And now we're able to put in values of t. We don't have to start from the beginning anymore. We can just feed them into this equation, put them in for all the t's you're seeing here, and the answer spits out a slope. So we kept getting better and better and better. But we realized when we subbed in 0.5, we got nothing. And we talked about that because you can't find the slope of a line if you subbed in the same point twice. Okay, so for instance, if I say the slope through 7, 2, and if I'm going to use that as my, here's my x1, y1, and my x2, y2, like if I'm going to use it for both, I'm just going to have 2 minus 2. I'm getting this indeterminate form. Okay, like you're not getting anything if you just try to get the slope using one point. Okay, so that's what was happening at our 0.5 here. So then it sort of brought us to this, and we didn't necessarily understand it. So we seemed like we were getting 13. And then at the very end of class, I sort of said, well, hold on a sec. That top actually seems to factor. And the T1 minus 0.5s are going away. So this is what was giving us our 0 over 0 problem. And as we put in 0.5, we did get exactly 13. So now that we know more about limits, this actually seems to make more sense now. Okay, we never needed a graph. We never needed to do all that chart analyzing. We could have just factored and be done in like 2 steps. Okay. So we want to formalize this. We don't want to have to start from scratch with every single new function we start with. So we're going to be skipping some pages here. So I think the next page you see is example 3. We're going to be skipping that. Next page you see, it's titled In General. We're going to be skipping this. You see another page, example 4. We're going to be skipping this because we want to get on to this page here. The title is more general. So I'll give you a minute to find that. Okay, so our goal, okay, so if you have some random function called f here, and a random a random x value a, what is the slope of the tangent? So what's the slope of the tangent at x equals a? That's that's our discussion right now, and how can we do that? So when you're at the point A, the y value is called f at a. You sub it into the function, it spits out a y value for you. So how can we get the slope of the tangent? Okay. What we're going to do is we are going to choose a point that's nearby. Okay, so I know this seems far away, but just for the purposes of being able to fit it all together, we're going to pick a point nearby that's on the function, and that's going to be called a plus h. The reason it's called a plus h is because we want to refer to the distance, the horizontal distance between the red and the blue point here as h. So h is the gap, I like to call it. It's not a mathematical term, it makes a lot of sense. H is the gap that's between a and a plus h. Okay? And so that blue point then has a y value. It's called f at a plus h. Okay, you're taking that x value, a plus h, and you're substituting it into the function, and it spits out this y value, f at a plus h. All right. So how am I going to get the slope of the tangent? So I want to bring you over to the Desmos interactive piece here. So here is our scenario that I've just set up in an interactive case. This, let me turn off, no, sorry. So the green here that I can turn on and off, okay? So green here is the tangent line. Okay, so Desmos knows what the tangent line is. So I've got the tangent line in there. Let's turn it off for a minute. If you have, let's bring this over, if this red dot is at the point A, and then the blue dot is at this A plus H, okay? So we currently have a gap between these two points right now, okay? How do you get a better and better and better estimate for the slope of the tangent? Okay, so let me put the real tangent back. So right now, okay, you're trying to make red overlap green because green is the answer. So right now, with this point being this far away, it's a bad estimate. But as we move closer, you get a better estimate. As we move closer, you get a better estimate. As we move closer, so just like we've talked about in advanced functions, as you move this closer and closer and closer, and you'll notice here the h. So this is we've got the program in here to know how big the gap is. So right here, when h is 1, look at the top left on the slider there. When h is 1, you can see that's a bad estimate. And when h becomes 0.1, so again, look at the left here. When h becomes 0.1, that's a much better estimate, but still at the end of the day, not very good. Like red is not touching green there. Okay? And so if h is 0.01 and better, red and green are not equal. And we're looking for exact here. Like approximate is not good to us anymore. We want exact. So the argument is as we, let me zoom out here again, sorry. As this point gets closer and closer and closer, as the gap, the H value, as the H value gets smaller and smaller and smaller, we keep getting better and better estimates. What happens when I make H equal 0? When H equals 0, okay, that's when I get the exact tangent line there, except we already know, we talked about it, that's not allowed. I can't get the slope. If I'm trying to find the slope of the line that goes through red dot here, I can't then also put the blue dot on the same spot. If you put it on the exact same spot, this happens. Oops, sorry. My slide that I wrote that down on go. Yeah, if you put it on the exact same spot, this happens. You just end up with 0 over 0, like everything stops. So what can be done? And this is where we need to know limits. Okay? So the argument is we want, so this gap here, so make the gap be as close to 0 as possible, not equal 0. Okay? If H equals 0, take a look, if H equals 0, well then you've just got A again. And now you've used the same point twice, and we know we can't do that. Okay? So how do you go infinitely close and not touch? Sounds like limits to me. Okay, so we're going to be using limits. So where did this expression that you're seeing here, this is, by the way, like this is the answer. No big secret here. You're staring at the answer. But where did this come from? Let's explain that for a minute. So I want the slope of the line that goes between the red dot and the blue dot. Okay, so there's a line that goes between the red dot and the blue dot. What is the slope of that line? Well, we know our slope calculation. So my y2 here, so my y2, trace it over, is this f at a plus h that you're seeing here. My y1 is my f at a. And then my two x values, right? My x2 was this a plus h that you're seeing here, and my x1 was a. So here's my, that's just what slope equals. That's always the slope between the red and the blue dot. That's what that means. And then if you look in the bottom, something nice happens. The a's actually cancel out. So it simplifies and becomes this, where it's just an h on the bottom now. So there used to be the a's, but they end up canceling. Okay, so you're just over h here, which is that gap, which makes sense because we know slope is the change in y over the change in x. Well, how much change in x was there? Well, that's the gap. So we went from a over to a plus h, so it changed h units. Okay. So here's our slope calculation between blue and red. Now, how do you make it be so that you're getting the slope of the tangent line? Now, this is where, so we take this expression that you're seeing here, and then we want to make the gap be on its way to 0, but not equal to 0. Look what happens if you equal 0. If you just put in h equals 0 right now, you will get f at a minus f at a on top over 0, which is 0 over 0. Okay? So you can't make h equal 0. That's not what I'm saying. What I want to do is make h go as close to 0 as possible, infinitely close, but don't actually get there. And that's where limits are our friend now. This is the time where I do my little mini rant of I have no idea why the people who wrote this textbook wrote it this way. Because in order to understand everything that's on this screen, don't you first need to have like a good understanding of limits? Well, why is this 1.2 and then limits were taught in 1.5? So it's, anyways, now you can understand why we skipped ahead, and then now we're winding back to this today. So here's our definition. So at the bottom of this page, you see 3 different definitions. So this first definition is completely valid, okay, but it's only good in certain circumstances. Whereas this definition, which is the one you see from above, this is good in all circumstances. So I don't want to have 2 definitions and one that's not as good. So we're going to focus on the second definition. The third one you're seeing here is identical to the second. It's just they're calling their gap delta x instead of h, just giving it a different name. Okay, so having said all that, let's put it to some good use. So your next page has find the equation of the tangent line to y equals root x. Let's change this up a little bit. Let's just find the slope. So we don't want the equation, we just want the slope. I want to change up the function a little bit. So it is root of 3x minus 2, and I want to find the slope at x equals 5. So I'll give you a minute to copy that all down. So here's some notation. Slope of tangent at x equals 5. That's a lot of words. How can we say that with math notation? We can say it by saying f prime of 5. So it's an apostrophe. Okay, so you're seeing it's an apostrophe between the f and the 5. And this is how we read it. So if you ever see f prime at 5, that's what I'm trying to say. Okay, so if you ever see prime, it just means slope of a tangent. Okay, so if you're doing f prime at 5, the slope of a tangent, well, if we look back to our definition, it says we want the limit as h goes to 0 of f at, in this case, 5 plus h. So our definition had, okay, our definition had a's here and here, okay, because that's at a general x equals a value. Well, we're not working in general. We're actually at a very specific spot, x equals 5. So our a's is the x value, x equals 5. All right, so that's just me copying down the definition from last slide. And now we got to go to work. Now it's a limit problem, and we got to answer this limit problem. So I'm going to bring it over here a little bit. So I've got the limit as h goes to 0 of, now I'll do these in separate square brackets here. So there's a purple bracket, and there's a green bracket. Let's do some school colors here. Okay, so, and don't forget, it's easy to forget sometimes, but don't forget this whole thing is still all over h. Let's start with the green. Okay, what is f at 5? Well, you're just putting 5 into the function, so that's the square root of 3 times 5 minus 2. Okay. Now, what is f at 5 plus h? So this is composition. So this is, there was some delta math activities related to this in our review. Composition is a replacement. So just like when I said f at 5, and you removed the x and put in a 5 instead, you're going to do the exact same procedure here. You've got square root and a 3. Now you are going to remove the x, get it out of there, and replace it with 5 plus h. So the x gets removed and gets replaced with 5 plus h. And then don't stop. There's still a minus 2 here. So you still have the minus 2. There you go. Okay, so f at 5 plus h. 5 plus h replaces the x there. So that's it in purple. Minus f at 5. That's it in green. And it's all over h. Now we can just take a step to just clean everything up. So the 3 will expand inside. And we're going to get the square root of, that's going to be 15, but then there's a minus 2 there. And the 3 will carry on to the h as well. So 3h plus 13. Again, it was 15 minus the 2 that was here. Minus, and then that works out to be root 13 all over h. So the thing about these slopes of tangent problems is they start with a definition that is a limit, like we did here. Okay? It's up to you to do the composition and a simplifying. And now, if you just look at where we are, this looks like a lot of the problems from 1.5. And that's all it is. This is now just a limit problem, and now solve it like you did with all the 1.5 limit problems. So let's check if it's indeterminate. h is 0 in there. That would be gone. You get root 13 minus root 13. That's equal to 0 on top. Put h equals 0 on the bottom. That's equals 0 on the bottom. So yes, this is indeterminate. How do we deal with limits that are indeterminate that involve square roots? We multiply by the conjugate. So I'll change it to a plus 13 in the middle. Okay. And so now, as with all these conjugate questions, nothing happens in the bottom. Just multiply. Okay, you're just doing h times this and leave it in a factored form. Don't expand inside. We want the canceling to happen later. In the top, we just have to do first and last because they are conjugates. So these multiply and the square roots fall off. These multiply and the square roots fall off. Hey, look, 13 minus 13. That was nice. So now it's just 3h on top. And then we've still got our nice denominator here. Now we can finally see why was this indeterminate all along? Because there was a factor of h in the top and bottom that were hidden. Okay, but we did all this work. They revealed themselves. So now we no longer have that problem. We have this new limit, and now we answer the new limit problem. Try to sub in 0 for h. That doesn't give any problems. Sorry. There we go. So now we've subbed in, so I'm no longer going to write lim in front anymore. So that's 3 over 2 root 13. You're getting root 13 here and another root 13 there, so that's 2 of them. Okay, so there is our slope of the tangent at x equals 5. Okay, and if you want to check your answer here, So in a decimal form then, this is, so we type this in, you get approximately 0.4160. Okay. We can use Desmos to check our answers. So I'll show you how that works. So 0.4160. If we come back here, let me get a new graph. So if I call my graph of x square root of 3x minus 2, so here's our function. Okay. If I want f prime, so again, you can just type apostrophe f prime at 5. It won't draw it there for you, but it'll just tell you. So you can f at 5, like you can just figure out what's the y value at 5. It'll tell you the value right here, but that's not what we're looking for. We want the slope of the tangent at 5. So you put a prime in between. Here's the slope of the tangent at 5, 0.4160, which is exactly what we had. All right. So at this point, here's an example you don't have in your notes, but I'd like us to try this one. So what's the slope of the tangent to this parabola at x equals -2? Okay, so pause the video if you'd like to get yourself some separate paper. So in order to start, I'm just going to grab the definition. And the definition, okay, I've got g's instead of f's, obviously, because it's g at x. And then wherever the a's were, now I've got -2 in place of the a's because I want it specifically at that moment. But at this point, I'll give you a small little hint. So when you are doing this, okay, doing this composition, this -2 plus h is actually going to replace both of those x's. So both of these x's will come out, and you're going to drop in -2 plus h in its place in a bracket. Okay, so please pause the video now so you can give this a try on your own, and then I'll just quickly show the answer and talk through the key points and move on to the next one. All right, so now that you've had a chance to try it, here's what the first line should look like. So again, you're seeing here, it was 2x squared. So now you're still seeing the 2. This replaced the x, but the squared is still there. Then it was minus 3x. Minus 3 is still there, but then the x got replaced by -2 plus h, and the plus 1 is still there. And g at -2, well, just put -2 in the function, it works out to 15. So there's your first step, just a substitution step with composition. Now on the third step is where we clean it all up. So we can square this bracket here, expand the -3 inside. This is the point. So this is the time where I remind you, please, please, please do not just put the squared onto both. Okay? That's the poster in my room that says you made a baby cry. Squared does not travel over plus signs like that. If you're squared, you actually have to use FOIL. It's this times itself. And then with FOIL, you get this trinomial down here. So that's this bracket squared, but you still haven't included the 2. 2 still then has to distribute onto all 3 of these. So we need another cleanup step here. Okay, here we go. So now we are, ignore that. Now we are here with this limit problem. Check if it's indeterminate. Well, put h equals 0 in. Yes, you get 0 over 0. Okay, I see an h common in both. Let's common factor. So there it is, your common factored. Hey, look, that cancels the h on the bottom. Here's my new limit. Sub in h equals 0, we get negative 11. So the slope of the tangent at negative 2 is negative 11. So these questions are very repetitive. You are going to use a definition. That's a limit problem. You'll sub in and clean up, and now you'll have a limit question that looks just like all the questions you did in 1.5. And answering that limit question is the slope of a tangent now. So you know the slope of the tangent at negative 2. Okay. So I know this video is starting to run long. We got one more example, and I'm going to do it similar to last one, where we'll give you a chance to try it, and then I will show you quickly so you can work at your own pace with pausing the video. Here's something a little different. Again, I'd like to change the question here, please. So instead of just 1 over x, let's make it 2 over x plus 7. And I want the slopes of the tangents at all 3 of these points. So negative 5, 1 is on this curve. So is negative 3 1/2. So is 8, 2. All 3 points are on this curve. I want their 3 separate slopes of tangents. So I'm going to ask you a rhetorical question right now. Do you want to have to use the definition when a is negative 5, figure it all out, then reset all the way back to the beginning, and then make a negative 3, and reset all the way back to the beginning and make a negative 8? That doesn't sound fun. So what we can do instead of doing this question 3 times in a row, what we can do instead is do it once in general, and then substitute in negative 5, negative 3, and negative 8. They are x values. So here's what that looks like. So we've got, try to keep all this on the same screen. So here's just the definition. I'm just taking this from the last slide there. Let me move this over so we can all see it as I bring it down. Okay, so here's our function m on the side. Now, our definition is the slope of the tangent at a, and a general a is this, just grabbing from the last slide. Let's leave it, let's solve this keeping the a's involved. Okay, so we're not going to put a number in for a, we're going to leave it as just the general a. So instead of 2 over x plus 7, I'm going to replace the x with an a plus h. Okay. Now we have a plus h plus 7. And on the bottom here, sorry, so the x that was here, the a plus h replacing the x right here. Okay. Give me 1 second, sorry. Okay, and we're back, sorry. So don't look at the purple for a minute. We'll need the purple in a second. So this first line is just substituting in. So we substitute in a plus h in for x, there it is. And then we have to substitute in a for x. So there it is right there. Instead of the x, you see I have a. And now, okay, now it's a limit question that's like 1.5. And it's fractions in fractions. So this is where we discussed we have 2 options. We can do a common denominator in the top here. Okay, but we talked about how that's the long way. The short way is if you multiply top and bottom by the common denominators, because now this carries itself onto both. And when it carries itself onto the first, the a plus h plus 7s get canceled, and you'll just have 2 times the binomial there. And when it carries itself onto the second, the a plus 7s cancel, and you'll have 2 times the trinomial there. And in the bottom, you just have h times this bracket times this bracket. You're not going to expand. Okay, so that's what it looks like on the next line. now we are going to resist the urge to cancel. It's very, very tempting right now to say, oh, those cancel, I'm done. Nothing cancels right now because of the subtraction that's happening in between. So don't cancel anything, even though it's tempting. The only thing we can do is expand this 2 inside, expand this -2 inside, and just clean it all up. So it cleans itself up there. We see a lot of things going away now. I see 2a minus 2a. I see 14 minus 14. So the only thing left on top is a -2h. And so now that h can cancel the h on the bottom that we didn't expand inside. That's why we kept it a factored form. We wanted access to it. And now we have this new limit problem. We can put in h is 0. And there we go. So that's the answer to our limit question. Yes, it has a's in it. That was expected. Okay, because this a is an x value, right? Remember, this was the slope of the tangent at x equals a. So this is representing all the slopes now. If you want the slope when x is 0, put 0 in there. If you want the slope when x is 1, put 1 in there. You want the slope when x is 99, put 99 in there. Okay? So we wanted the slopes at, okay? We wanted the slopes at -5, at -3, and at -8. So you don't have to reset all the way back to the definition anymore. You can just say, put -5 in there, slope is -0.5. Put -3 in there, I'll let you work it out. Put -8 in there, I'll let you work it out. So the strategy we did on this slide is a really good one when you need the slope in general, okay? Because we wanted to get the slope at 3 separate points, we didn't want to do this problem 3 times over. So instead, we did it once, okay? We did it once in general for an a value, just called it a, worked out the limit 1 time and got an answer with a's in it. And so now that's the general slope. And so now we can just put in -5 and work it out. The answer is a slope now. Put in -3, you'll get a slope. Put in -8, you'll get a slope. Okay? So, yes, this was a long one. My apologies for that. It's sort of the culmination of this entire chapter, really. The reason we're doing limits is so that we can answer that seemingly impossible question: how do you get the slope of a tangent that's not just an estimate, that's as an exact value? And the way to do it is with limits. So we learned all our limits, and now we've formalized it using the definition we have in 1.2. So at this point, you can try the 1.2 delta math problems that are assigned, and have yourselves an awesome weekend. I'll see you on Monday. And if you have any questions, feel free to email, please.